Okay, hello everyone. I think some of you are missing. Okay. All right. Anyone still need the authorization code, or I think yesterday there are 2 students. I think I already gave them, so I think it should be okay. So yesterday we discussed on. So our discussion is about the arc length, right? Arc length function. Basically, we measure how long the curve. Right? So if we are given like some random curves, if we could interpret the curves in our xy Cartesian, then we could approach the measurement with integrations. It's similar when we think integral as approximation on the area under the curve, right? Area under the curve. This is pretty much almost similar, but we are limited on the segment. Okay? We add all the segment that we cut from the curve, and because of the addition, then we call that or we approach that with our integral, right? Okay. And we also learned that we could represent the arc length in a function, okay? Like we did before here. For today's class, we want to move on to the second section in chapter 8, which is the surface area. So let me start for today's class, okay? So I think after this class, I think I will give you maybe some small exercise for you to review, but later on, okay, I think I will post in Moodle. So if you look on the surface area, okay, so if we take, for example, let me just write area. Let me write the title. And suppose we are having the curve. Let's say the curve is just like this. Okay, it's a simple curve. And I would like to do some review for your calculus. Okay, so if we want to, if this curve rotated on x-axis, okay. So imagine, okay, if this is from A, and this is B, okay, and this is our usual functions, f of x. Now we could imagine that the curve will rotate. Let's say it goes through here. It also has its rotations, and we get some sort of volumetric shape, right? It has volume. Okay, it's a three dimension, it has volume. And based on what we did in Calculus 1, if you remember, that if we slice, okay, so again, the approach for any integration is to slice the curve, okay? Okay, slice the curve. So we slice this, and suppose that we have this small segment, like where you could imagine that this is like a cake. So you slice a cake, or you slice some fruits that is symmetrical. So you slice it up, and you could imagine that there will be some small distance in here, like this. Let's say this is the x because it's on the x-axis, and we have the radius here, right? So basically, it's just a geometric perspective. So we have a radius. So basically, what we did in Calculus 1 is we are adding all the segments, right? All the segments. So we just find this volume, which is this area. This is a circle, right? This is our r, so pi r squared. And then multiply with what? with the height, right? So similarly, if we imagine, okay, if we imagine this shape here, and now our goals, okay, our goals is not to find the volume. Okay, we want to find the surface area here. Okay? That's so. For example, if we imagine a hollow tube like this, okay, if we slice this, we cut open, we could make it into like a rectangle. Okay, if we make this into, let's say we have the radius here for the surface area for the circle, we have the height. Okay, we make this and we can put the height and this one, and this is the circumference for the circle, right? 2 pi r. Okay. So what's the area? We just multiply this 2. Okay. Now similarly, what we are going to do is we are going to cut open. Okay. But before we are doing that, we need to make some approximations for the geometric, okay, for the geometric perspective. What kind of shape that we want to approach. Okay. Now if we, maybe different shape that we are going to take, maybe here, we have a cone. Okay. We have a cone. Okay, same thing. Like imagine like you are having a birthday party, right? Maybe when you still in elementary, you make your hat by yourself, right? You cut and then a birthday party, and then you cut open. Okay, cut open. We would like to see. Then this is the geometric shape. So if we make this size here, it's L, okay, and this part here. So if you imagine that if we put this and make it into a cone, the circumference is this part here. We call this is the arc, a circle, right? So this is L, 2 pi r, and we have an angle here. Okay, because we know that this angle is needed because this is practically a cut of a circle, right? So if we imagine that this is a full circle like that, okay, so this is only some percentage of that circle, which means that we can make this theta over 2 pi, right, for that area. So the area of circle is just a pi r squared, and now the radius on this side, the radius is this side. Okay, not to confuse with this r here. The r is the radius for this circle, and we have now a big circle, right? Okay, so let me write here the area then becomes theta over 2 pi multiply with pi and then L squared. Okay, everyone agree, right? And then I think I need to let me make here and let me make here. Okay. So we can solve this and simplify it. Becomes half L squared theta. Okay. And the theta, okay, we can also simplify, okay. Remember that this is a big circle, right? So this part here is also part of a circle, a circumference of a circle. Okay, so we could take this, that we could take the ratio between theta over 2 pi, okay? Or let me just write directly here. Let me write directly that L theta is equal to 2 pi r. So we could substitute theta is 2 pi r over L. Okay. And then we could make here half squared, and then this will be 2 pi r over L. So this can be written as, or maybe let me write here that the area is equal. So after some simplification here, over there, so we have the area is pi r L. And I think this is, I think high school, right? High school, right? Yeah. Okay. I think the cone, I think already good shape. Okay? If we can imagine that some curve, like for example here, if we could imagine, well, we could think that this curve probably the cone almost fit with our shape here, right? But the cone is more rigid, right? It's not like having flexibility like this one. What we are going to do is, because we want to slice this, right? We want to slice this. So we would like to find the criteria for our shape is we want to find the shape like this, at least this 1 segment here. What kind of shape is that? So imagine that maybe if we look at our cone, maybe we can, if we cut the cone here, maybe the profile a little bit similar, right? A little bit similar. If we cut this, those segments is similar to what we are having in the curve, right? Okay. So what we need, or maybe let me wait if you want to take notes for this. I think this is just a basic geometry, right? But the interesting part is the next part, which we are going to cut the cone. Okay, so cut around here. So we are going to cut here. I will show you in the next page. Okay, now this is what we are going to approach. Okay, we want to know what is this area, okay? This part here, the surface area. Okay, how to do that? How to find the surface area? The first thing is we know the cone, right? So there are two cones here, the big one and the small one. So let's subtract both of them. So the big cone minus the small one. And all the description, the radius already there. We have L, L1, so we could have some calculations for, or some formulations for the surface area. So let's start with the big cone. So big cone start with the area is, the big one is the R2, radius 2, right? So the area is pi R2, right? And then the L for the big cone is L plus L1, right? According to our area before in the previous page, okay? And now small cone, the area is R1, right? P R1, and then L1. Maybe L1, okay? Now this type of shape, this one here, this is what we call frustum, the name. Okay? I'm not sure why they call frustum. Maybe if you find out, let me know. Okay, I haven't looked yet. Okay. So the frustum, so area or area of frustum is basically the big cone minus the small cone, which is let me just write one by one here so that you know how to operate this. This is big, this is small, okay? So let's minus this, subtract. So area of frustum is pi, and then R2 minus R1, L1, or if you want to make sure, we could just take this, okay, and then make sure that our formula is correct. And then what else? Plus pi R2, why pi? This should be pi R2L, right? Oh, I missed the bracket. Let me move here and maybe here, maybe there. Okay, I think better. Okay, but still, we want to make our approximation or our approach more simplified. Okay, that's what we want. So perhaps we need to do something with the with R and L. Okay? What is our connections between all of them? If we look carefully here, let me make it smaller. Okay. If you look carefully, this is a triangle, okay? And I think we can do something with those triangles. Okay, we could make a ratio between those two triangles, right? So we can make, let me write here with the blue. So the small one, okay, and the big one, okay. And then from here, I think and then we can simplify it. Okay, and then let me move some R2 L1 minus, right, minus R1 L1. And then this is what we have. So this R2 minus R1 L1, okay, we could exchange to R1 L. So let's do that. So this will be pi R1 L, right? And then plus R2 L. Or we could take the area pi R1 plus R2 and then L, or pi L R1 plus R2, it's the same. And then we could take our simplification again. So let R be the average radius of the shape, okay, of the shape. So R is half R1 plus R2, okay. So R1 plus R2 equal to R. And as a conclusion, our area become 2 pi R L. And this will be the main formulations in our computations for the surface area. Okay. So the basic is from this formula, and then we are going to combine this with our integrations, okay? Because we are going to slice and then added all the surface area, okay? So of course we need integral, okay, definitions. And of course, how do we get L? How do we get L? L means if we have the curve, okay. If we have the curve, let's say we have like this. If we cut open like this, okay, L is here, right? Right? L is here, right? If we cut open, right? So how do we get L? Huh? Derivative? Why? No. No. Okay, L is just what we learned yesterday. The arc length. So we need to have the arc length formula inside here. Yeah, but that will be the next page, okay? Next page, we are going to see. So we need to find this distance here, okay? That will be our component in finding the area. And then the rotations, it can be here and it can be this way also. Just change the notations. Okay? Just change the notation. You will get used to somehow, okay? So if we finish chapter 8 by today, I mean the arc length and surface area, we could continue chapter 10 next week. And maybe if we need some review, I will review this. Especially, I think you need to refresh some of calculus 1 techniques, right? Yeah. Okay, now if you look at this image here, okay. So let's say that this is our curve, and we rotate that curve, okay, and we want to find the area of the resultant, okay? This one. Okay. And the way we do it, we slice, and let's just make some point here. Sometimes, okay, I also have some experience when reading some mathematics notations. If you are not familiar, like if you read like, oh, why is having this? This is just any point. Just want to make some. Okay, let's make the name pi minus 1. But yeah, I also find like why they name with this, but this is just to make it easy to compute. Okay, you can exchange that with other point as well. If you want to change with a, b, with the same thing. Okay? The important thing is the process. Okay, if we understand the process, then we know how to. Okay, we know how. Okay, now, okay, let's say we are going to see that the L. Okay, so L, this one here, L, right? The L is a distance of pi minus 1 pi, right? This distance between these 2 points, okay? And then, based on what we do before, we could take the average radius. Let's say r. Remember, our radius means the one that is in a circle. Okay? So of course, this is related to yi and yi minus 1. So half yi minus 1 plus yi. Yi minus 1 is maybe here, okay, right? If you it doesn't mention in the picture, but I will write here. This is yi minus 1. So remember the formula before, we have 2 pi r L, right? So basically, this is yi minus 1 plus yi over 2, and then distance of pi minus 1 and pi. And then we know that from the previous lecture yesterday that the distance is our arc length, right? Arc length formula. This will relate to the square root 1 plus, and let me use some sample point, which means that we can take this in any point, and then squared, and then delta x. So we exchange this distance, the area becomes or let me write from 2 pi and then distance. This is equal, or let me write with approximating 2 pi and then this one here, we did something here, right? So we could take that as our average radius, and our radius is the height of the curve, right? Or you could say the function itself. Okay? Okay? So because we, from previous page, we say the radius, and radius related to the circle. I hope you can catch up which radius what I mean, okay? which radius. Okay? The radius here is those one, right? And that is the function, right? F of x. Okay, the height of the function, right? Okay, f of x. We could say f of x. So we could say this is the average one. I mean, right here, average one is just the function. Let me write with the asterisk to make sure that it is a sample point. So we can write the f of x, xi asterisk, and then take the square root 1 plus f prime squared, and then delta x. Okay, it's I think almost done. Okay, but remember, this is just our one small segment, right? We need to plus from to all shape, okay, for all shape or segment. So we are going to use the summation. And then take limit, right? Take limit. As the n getting larger, it means that the small segments getting really large, okay? Large number. And whenever you see any limit, and then the summation, the sigma, you can think this like integrations. Definition for integral. So if we are going to evaluate from A to B, okay, so if the A and B is our endpoints, then this is practically an integration from A to B, and then 2 pi f of x, and then multiply with the arc length, okay? And then dx. So the way you do this surface area is you can start with the arc plane first. Start with the arc plane. Or if you would like to combine like from the arc plane thing, you can do it inside. So you can find the first derivative of the function is squared plus 1 and then square root and then put here. Okay, put here. And then you can try to find out the result from the integral. Yeah, so there's at least 3 or 4 steps on working on this surface area. Okay, note that this is when we rotate the curve on x-axis, right? Because what we did here is rotating on x-axis, okay? This is rotating about x-axis. Or let me write completely rotating a functions. The functions is f of x. From A, I think I written here, from A to B. So of course there are another part that is rotating about y-axis, right? Okay, if this is rotating on y-axis, then it will be dy, right? It will be dy. So if you imagine, before it's just like this, right? If we rotate with y-axis, it goes like this. It goes to be y. The dx becomes dy, and all the functions become function of y. Okay. 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 Now is, let me check whether I have another page. Oh no. Oh, here. This is a conclusions, actually, conclusions. Okay, so what we did is rotation about x-axis. So to summarize our surface area, so this 2 pi y is the circumference. this one here, right? So imagine like cut open. This is our circle, and y is radius, okay? Or y, if this is function of x, then y is f of x, okay? And ds is the arc length, right? The arc length, the length, the distance here, the one here, right? And if we rotate about y-axis, okay? So this will be our radius, okay? X. So we can write x, and maybe if you would like to write in function of y, like g of y, we could also do that. Okay. Now, of course, the ds, okay, the ds should be in the same variable with the one that we are going to integrate. Okay. For example, if this is function of x, the ds should be on dx. Okay. And this part also should be on dy. Okay. So the way we, like the square root 1 plus the derivative, right? You need to also define what kind of derivative. Is it derivative of x or derivative of y? Okay. And that's when you can decide which one is dx, which one is dy. Okay, I think we can have some examples, right? And also, if we still have time, maybe just an introduction on chapter 10, just a little bit introductions. Okay. Then we can start with, let me check first. Okay, let me give you an example here. Find exact area of the surface. Obtain by rotating curve about, so number 1 is it's on x-axis. The curve is y equal square root 1 plus e with power of x 0. Let's try whether this is difficult or not. The second one is rotating about y-axis. Or maybe the same x-axis. Let me write 3 examples. X-axis. But the equation is x equal 1/3. See if you can solve this. Okay. And this is from 1 y. Okay, we are going to have a short break. Okay. Okay. All right. Anyone try? Okay. Okay. So. Okay. Okay, I have 2 questions. They are the same rotations on x-axis. The difference, the first one is, I think, like a regular previous example that we did. Like this function is also in the function of x, but the second one is the function of y, but rotate on x-axis. Okay, we will see how to deal with this step by step. Okay. Now, first thing is we are going to remember that every time we are dealing with the rotation on x-axis, we are going to write just a normal as, this is integration, let me just write a simple one, 2 pi y ds, okay? Just write this. This is really helpful. Do not write like the final one, like dx dy. Okay? Just write the basic one first, okay? Because we are going to set out and to decide whether we are going to use dx or dy based on the question and based on the formulation here. Okay. So we have integration 2 pi y dx. Okay. Okay. To differentiate these two, the first one, the y itself, we can substitute with the function of x if we want to make it dx. And I think that will be really helpful. Okay. But the second one, we could have choices. Okay. We could make in terms of x if we want, or we just write y with this y, and the problem will be solved. And when we decide the dx, okay. So the dx for the second one can be dy. Okay. Now let's start with the first one. Okay, let's start with the first one. So we can find the derivative first, right? To make it into our ds. So the derivative, so let me write, let me make a space here, around here. Okay. Okay, so we have y equal square root 1 plus e with power of x. So we would like to have a first derivative, okay, y prime or dy dx, okay, is if I write e to the x, do you feel this is too fast? Too fast if I write directly that? Okay, let me give you a tips. Okay, this is also a tips. Okay, if you have a square root of x, if you want to derive this, becomes this, right? Okay. Now, if you remember the chain rule, if I make this 4x, okay, this will be 4. Okay. Okay. Now, if I have the square root of 1 plus e to the x, this is the same thing. Okay. We are going to make this into the same formulation with 2. Okay, and then this will be the chain rule. Let me write one by one. And that's why it becomes this. Okay. Or if you still need to make from the scratch, then to make more convincing, maybe you can also start from this. Okay, and then we write the derivative and make it half going here, and then 1 plus e to the x, and then half minus 1 is become negative 1 over 2, which we are going to see that this is the same, okay? Where the square root here is coming from this minus half, okay? So this is my tips. Every time you see any square root with some function of x, okay, for example, and you want to derive that with respect to x, what you need to do is bring those down, multiply by 2, and to the chain rule of this. Okay? If you're already familiar, you will get pretty fast. Okay? No need to make this happen again. Okay? So you can skip one or two processes because this is elementary. Not really in our topics, but we need to compute that. Okay? Now we have this, right? And then we need to take squared, right? Take squared. So we are going to square this, right? Maybe and then we plus 1, right? And then we take the square root. Okay, we take the square root. So let's say we are going to square this, so e to the x become e with power of 2x, like that, right? And then 2 with power of 2 is 4. The square root is cancelled, so we have 1 plus e to the x, and then plus 1. Okay, and we want to make square root now. So I hope everything clears here. Okay. Okay, I think there is no other way aside from we need to plus this 1, okay, with all thing here. So let's make that happen. So we take the denominator. Let's say the denominator is 4. Let me write with 4x like this, 4ex. Okay. So that is the one that we are going to plus on the top, right? So plus 4 e to the x. Okay, and this is with the square root. So we still have the square root here. Okay. And maybe we make a factor again like the previous one. And then this part here, well, the thing is, we need to observe, like I said yesterday in arc length, sometimes when you see the square root in an arc length formulation or computation, sometimes the one that's inside, if you see like it's still complicated, maybe we could simplify it, and maybe we could make the squared form from this equation. And I think we can, right? Because this has squared here, right? And perhaps this is have relations. So if let's say we have the e to x, okay, and then we have 4 e with power of x, and then plus 4. So this is comes from e x and then squared. This is comes from 2 squared. So perhaps we can combine this together. Okay, if we take the ex plus 2 and then squared, and I think that is how we can get 4 ex. 2 by 2 is 4 and e to the ex. Okay. So I think this is the form that we can conclude from this equation. And how to get this is actually you need to get into habit. Okay. If you look at the form, my tips is every time you see the square root and something happened here, and you might think that this is related to the quadratic formula, perhaps you can simplify that. Okay. That's my tips. Okay. And I think it's frequently happen in the problem solving. So we could make this into the ex plus 2 squared, right? Oh, I forgot the square root. And then 4, 1 plus e to the x. Okay. That is 1 plus dy dx squared. Okay, I need more space. Okay, I think we can simplify. We can cancel the squared with the square root. So we could write ex plus 2. And then square root of 4 is 2. So we could write that. And I think we could just write square root 1 plus e power of x. And you will see that this is the same function as we did in the previous question, in the original questions, right? And we need to multiply this. You will see that it will cancel, right? Right? Okay. So let me write as is integrations from what? 0 to 1. Okay, we are going into taking into dx now. So now we decide, okay, which integration we want, dx or dy. Okay, since all information that we have is on x, then perhaps x is our choice. Okay, so let's say we have 0 to 1, and then here 2 pi y ds, right? 2 pi y. So 2 pi, and y is f of x, and our f of x is this. Our y is square root of 1 plus e to the x, and then multiply with ds. ds is this, ex plus 2. But because we already entered the integrations, then we need to add dx at the end. Okay, so it's nicely cancelled out. So what you have is pi, I'm going to write integrations, e to the x plus 2 dx. Okay, I hope you can catch my idea here. Okay, if not, let me wait for you to take the notes and see the idea. Okay, and then from the integration here, it's pretty easy integrations. So we could take e to the x, and then 2x like that. So this will be pi e plus 2 minus 1. Or pi e plus 1. Okay. Okay, number 1 done. I think the problematic one is from here, right? Because the surface area itself, I think not too complicated. I mean the formula. It's become complicated because of we need to derive, we need to square those results plus 1 and then take the square root for the s, right? For the s. Okay, any questions? Any questions? Do you think it's too fast? A little bit too fast? A little bit. Okay. Okay, let me slow down. Okay, let me make here. Okay. And another tip is every time you see some solutions, you need to try out by yourself. You cannot just understand it. You just look. Maybe if you're a genius, maybe you can. But sometimes most average people like me, I need to try if I understand. If I'm still not understand, I need to find another resource for me to understand that part. So you need to try. You need to try to find which one is your limit. Oh, I don't understand this. So I need to study that part. Okay? So if you saw something, and I believe in YouTube there are a lot of tutorials that you can find. In English, I think in Chinese there's also a lot, right? Have you checked? I haven't. I checked the English one. But I saw some Chinese one. A few. Not sure whether they are good or not. I'm not sure. Not sure. But usually I saw and just look at how they write. If I understand, okay, maybe it's good. Okay. Questions? No? Sleepy? Yeah, it's normal. You need oxygen. Because maybe processing in your brain, it takes much energy to process your brain than your body. Do you know that? Yeah, it's true. If you learn biology, it needs like a lot of energy in your brain compared to your body.
So there's no need to go to the gym. You can just study.
But it's different thing. It's different thing. The energy is a little bit different. Okay. You need to also do exercise. Find something interesting.
Number 2?
Yeah. Number 2 is a little bit tricky. Hmm? Do you think so? Do you think it will be more complicated or no? Or you can keep y? If you have to keep y, then you need to write y. So you formalize have y, right?
Yeah.
So you can keep that y. No need to make it into the x. Yeah. and you just need to solve the arc length, okay, in the dx over dy. Okay. Okay, I will go to the next round. Okay, next round is this part. I think I need more space, so I will copy to the next page. Anyone still in taking notes here? I can wait for 1 or 2 if you need. I think finished, right? So let me write again here. Okay, now it's still rotation on x-axis, okay? So we still write as, let me just write the general formula. So 2 pi y ds, okay? So this is to help. Okay? Sometimes if you make early conclusion dx or dy, maybe you will find like in the middle and you realize, oh, maybe I did something wrong and you need to go back to the square one. If you write the general formula here based on the rotations, it will help you to design which path you are going to take. Okay? So you take this 2 pi 1 ds, and then we need to decide from the x which one ds, because our functions is, I think, function of y, right? If we make those functions like we simplify and make into function of x, it will be taking much time, and maybe it's not solvable at all if we take that route sometimes. So I think we keep that function as a function of y. So what we are going to derive is we derive with respect to y. So dx over dy. I think that's a better choice, okay? Wise choice. If you make switch x and y, and maybe messy. Okay, so we are going to take dx over dy, or the derivative with respect to y. So we have here is, or let me write one by one. Let me write d dy, and this will be 1 over 3 y. I think, let me write here. 1 over 3 is a constant. Let me write outside. So d dy y squared plus 2. Okay. Now derive this. Okay. 3 over 2 going to the front, right? And then minus 1. Okay. And then don't forget to multiply with the chain rule. So let me write one by one as a refreshing the calculus one. Okay. So 3 over 2 goes here. Y squared plus 2. This is minus 1 is half. And then the chain rule. I will write one by one the process like that. And then we can cancel that out. So half y squared plus 2. And then this chain rule is 2y. And also canceling this out. So finally, we get y squared plus 2. Okay. Or you could write with a square root y squared, square root y squared plus 2. Okay. I think it's a regular derivative, but it's on y. And then we could take this square, right? And then plus 1. So this becomes 1 plus dx over dy squared. So this will be y squared y squared plus 2 plus 1. Okay. Okay, can we simplify this? I think we need to check. Okay, we need to check. So y power of 4 plus 2y squared plus 1. I think this is quadratic formula, right? It's quadratic formula, a squared plus b squared, right? Can you see?
Yes.
Okay, yeah. So if you have like this, it's the same, right? So we have the y squared plus 1 squared. So every time you see the r-plane, the square root, most of the case, you need to do the simplification using the quadratic. You need to find the squared form of that formula. And that's my tip. Because if you are blindly using the formula, and maybe the algebra part, you will be confused how to solve this. I mean, oh, it's too complicated, blah blah blah, right? So we need to adjust the perspective that there will be some simplifications. Okay? Your textbook, most of the problem, they are easily to process, okay? Except the approximations one. They are using some decimals. But the other problem is, I think, it's like a smart question. Okay? So of course, the way you answer need to be smart. Okay. So we get this. I think we need to square root, right? Square root. So we can square root this, that. Okay. And then simply we can just cancel the square, and we say that this is equal to y squared plus 1. Okay, now this is the part that we are going to substitute. Okay, let me wait if you want to write first.
SPF over dy.
Yeah. Yeah. Yeah, the x over dy. So that means the way we integrate the whole solution, the surface area, dx over or dy is not related to the rotations. Rotation can be in x-axis or y-axis, but dx or dy, it depends on the functions. We are the one that decide. So if this is the one that we decide, y, then the whole process will be in dy. Because dx can be dy, can be dx, right? Yeah. So back to here, okay, see. So the difference on the rotations, okay, on the rotations, if it is x-axis, it has y here. The difference in the radius of the rotations here. The radius for the x, you remember, we have if we rotate here, right? So this is the radius, right? So radius is here, which is, what's this length? Y, right? Okay, y. Okay, so this is y. Okay, the first question we are having in a function of x. Okay, so when we multiply into this equations, then y we can change into function of x. But now, our function is a function of y. So we keep this y over there. Okay? And then the surface, and you can also conclude from the information, it's give you just only y. Okay, perhaps that's going to be dy, but sometimes there are some tricks too. But for now, perhaps we need to aware, or maybe it's in dy. Okay, maybe in dy. But the decision is after we solve this. Okay, and you can decide dx or dy. So this will be dy. So 1 to y, 1 to 2 for y, and then 2 pi. Keep dy over there, and then ds is this results and multiply with dy, right? So y squared plus 1 and then dy. Okay. Let me factor 2 pi because it's a constant. So we would like to have y cubed plus y and then dy. Okay, I think that's pretty standard integrations. So this will be 1 over 4, y with power of 4, and then plus half y squared from 1 to 2. I need to do some calculations to, what is this? 16 over 4. So 2 pi 4 plus 2, right? And then minus 1 over 4. This is plus 1 over 2. This is 6. This is 3 over 4, right? Half plus oh yeah 21 over 4, right? 21 over 4, and then multiply with 2, it's become 21 over 2 pi. So the rotations for different axes, they will have the difference in the 2 pi y or 2 pi x. Okay? So all these two questions, they both rotate about x. So we write 2 pi y. Okay? So 2 pi y ds. Okay, just write x equals that first, and we decide which dx we are going to use. Because we can also have dx, we can also have dy. Because sometimes, if you misunderstand the previous slide, the previous lecture, maybe you will feel that, if we have 2 pi y and y is function of x, then the x will be the x. And the other one is 2 pi x and it should be function of y and it should be dy. No, that's not the case. It can be both the x or dy. But the way that make differences is this one, x. Okay? So 2 pi y dx for x-axis rotation, 2 pi x dx for rotation on y. Okay? Okay? And that's the important one, the principal one. Okay? The rest is you need to more have practice, okay? Especially observing the quadratic, some algebra over there, and some techniques for integrations. But usually, if they already give like a complex one here, the integration at the end should be not too difficult, should be. Usually, they will keep the balance in the question. Yeah, mostly. Most of your question in the textbook, that is a direct question. I think most of the questions like that. Okay. Any questions? Any questions? Okay. I think tomorrow is your TA class, right? I think your TA will also have some practice on the arc line and surface area. Okay.
My brain is dead.
We'll just start with chapter 8. Remember, all the techniques like you learn in calculus 1, derivative, right? All the techniques in derivative, integrations, finding the area, finding the volume. Okay, we are going to see that in the future in calculus 2. So, arc length and the surface area, we are also going to use these techniques in the future, especially the chapter 10. The chapter 10, we are not dealing with the x, y. We are moving the x-axis and y-axis, and we add one variable t. In physics, I think you're familiar with you have a distance, you have velocity, you have time, right? You have time. Now we are going to use that x and y distance, and we are going to see time, t. So it's like when you move from one point to another point. Okay? And in chapter 10, we are dealing with t. So all the integration, all the formula, or the derivative, all with respect to t. We are going to find the relations between the x, y, and t. Okay? That will be the next week. Okay, next week course. Okay, any questions? No? If no questions, then I will ask the questions and I will give you the question. Okay, as usual, and I think for some of you who just take this course, the calculus, so usually every day or maybe at least one time every week, I will give some like an exercise. You can say like an exercise to see whether you can solve the problem and whether we need more practice or review in the future. Okay, so I hope we can do that. So I will end the